Hello, everyone. Welcome to our GDSC event called the $5 million question. $5 million question? How can we make quantum computing useful? My name is Jana. I'm GDSC lead at GDSC UoL, and today I will be facilitating this event. With me today is Petar. Petar is a software engineer whose career spans for more than 2 decades. He's been programming on a low level as well as implementing complex system. He is a founder of community that is promoting quantum computing, which is called Quantum Serbia. He is technical consultant at the Quantum Computing Institute, Cape Town, as well as the lead at the computing software startup called Quantastica. So welcome, Petar, and I hope you will enjoy this session in which we will learn about quantum computing, and in the end we will have a hands-on lab that I encourage you to stay for to see how real quantum computing works. So welcome, Petar.
Thank you, Jana, for the introduction, and hello everybody, and thank you for joining this call. Let me share my screen to show you my presentation. Okay, so today we will talk about quantum computing, and so this is the plan. What we will learn today, we will learn what is quantum computing and why do we need quantum computing at all. Then we will demystify quantum programming. We will have a crash course of programming quantum computers. And we will see how all of us, how we can contribute to a useful quantum future. So how we can help quantum computing to move forward and to make a positive impact on society. And after this main session, we will have extra session, which will be hands-on code example, where I will solve one very simple problem on a quantum computer. So this is the plan, and let's go. I have many slides in this presentation, so I hope it will fit into 1 hour. So let's start. Let's go. What is quantum computing? Before we move to quantum computing, let's talk about unconventional computing. So let's talk about what is motivation for unconventional computing, or why classical digital computers are not enough. So we have classical digital computers reached limits in terms of problems that classical computers can solve. So we have every industry have problems which are not reachable or inaccessible to classical digital computers. So we have very, very complex problems, and this is happening in every industry. And in order for humankind to move forward, so progress to move forward, we need to solve those hard computational problems. This is main motivation, and other motivation could be that we have the demand for information processing is ever increasing, and it's accelerating. So today we have a significant use of energy, of total energy produced is used for running data centers, and this is increasing every day. With artificial intelligence, which is boom last few years, we have even higher demand for information processing, and we need to think about alternative ways to perform computation. Now, so we need to solve complex problems that are and will stay inaccessible to classical computers. There are problems that are simply too complex to solve, and we will never have a classical digital computer which will solve some hardest computational problems. Its motivation is to perform what digital computers are performing today, to perform faster, with lower cost, with less energy consumption, and with better quality or precision. So these are motivation for thinking about unconventional computing. And this graph here is, I believe that everybody in this call are people from information technology, from information industry, and they all understand what this graph means. We have easy problems, so these green lines are easy problems, problems easy to solve on classical digital computers, which have, for example, this green line have constant complexity. Then we have higher and higher complexities, and these red lines are challenging to solve. And for example, this leftmost red line has complexity too high for any classical digital computer, and when as problem size increases, the time required to solve the problem is too long, practically impossible to solve problems which have this factorial complexity. So we need to think about unconventional computing, and there is multiple approaches to unconventional computing. Some technologies are already commercialized, like this Fujitsu digital annealing unit, which you can see in the picture. This is actually specialized optimizer, but this is still digital, and it's similar to classical computer, except it is using some tricks, and it is specialized for solving combinatorial optimization problems. But there are more, more radical approaches, like searching for inspiration from nature, how nature is doing calculation, like chemical computing. There is bacteria. Bacteria are performing some operations which we possibly could use to perform our calculations, and so on. So research is going in many directions, and one of the directions of unconventional computing is quantum computing. So what is quantum computing? Quantum computing is a technology that is using the laws of quantum mechanics to solve problems that are too complex for classical computers. And at these pictures, you can see at the left side, you can see Google superconducting quantum computer. And at the right side, you can see IonQ. IonQ is a company who made trapped ion. So this is ionic quantum computer. This is two different technologies of quantum computers. And so quantum computing is the use of quantum mechanical effects to perform calculations. I will explain more. I will explain how that works and how what potential it has. the potential of quantum computing is easy to see on this picture. So we have different complexities from exponential, which is most complex in this picture, and going to constant complexity. And green lines are showing, and green and red lines are showing some quantum algorithms, some common and frequently used quantum algorithms. And you can see that some quantum algorithms can transform or can perform calculation which has exponential complexity, can perform in constant time. So this is most extreme example, and other less extreme examples, for example, the Simon algorithm, Grover search, quantum Fourier transform, and so on. We have speed up. So there is a quantum algorithms are offering speed up over classical algorithms. Now, if you understand complexity, then you understand how big impact this can have on every industry. Something that takes hours or months or years to calculate. For example, if this exponential problem, it can be calculated in a split of a second on a quantum computer. So this is the potential is very high, and because that high potential, impact on industry could be huge, and this will be impact on almost every industry. I listed only a few industries here, like healthcare, chemistry, energy, transportation, logistics, and finance. For example, in healthcare, we can use quantum computers to calculate molecules which are cure for some deadly diseases. We can make personalized medicine, which is by calculating molecules which will interact with proteins in human body and so on, which is different for every patient. In chemistry, we can make new materials and some catalysts for chemical reactions and so on. In energy sector, new energy sources which would be good to have, because energy is a big problem today, energy production and storage. Also, for example, better batteries for electric vehicles and so on. By calculating molecules that could perform better than current batteries, for example, if we are talking about batteries. But anyway, in any industry, there are high problems with high complexity, which quantum computing could possibly solve and move that industry significantly forward. So that impact could be huge. And because impact is potential impact is high, is big, industry is already preparing. And I assembled only a few examples here. This is not a full list, but for every industry, I listed some companies that you are familiar with. All these logos are very, familiar. And mostly big companies who have a budget for let's say unconventional approaches to their problems. They're already started preparing, and they are already experimenting and assessing the potential use of quantum computing in their everyday business. Now we have customers, we have users of quantum computing. We also have providers. So who are providers? Providers are both big tech and startups. And again, you have some familiar names, at least in first row. There is Google, IBM, AWS, and Microsoft, which are big tech companies. Apple is not yet in the game, at least as far as I know. But so big tech is other big tech companies are already experimenting with not experimenting. They are offering services to those companies, and they're also. For example, Atos is European company, let's say European big tech, and we have some startups. Some of those startups became publicly traded companies like D-Wave, Rigetti, Quantinum, IonQ, and other smaller but still strong startups who are operating in this area. Most of these companies also have hardware, not only software, but some companies have only software, like Quantastica. So we are only in software. We don't have our own. We didn't develop our own quantum computer. We are developing software for quantum computing. So we have customers, we have providers, and in some conferences, in previous conference when I was talking Data Science Conference Europe in Belgrade, after my presentation, people asked me, "Do quantum computer really exist?" And I was surprised for that question, but yes, quantum computers do really exist. And not only that, you can use quantum computer in a cloud in this first row, and not only this big tech, but some startups also offer a quantum computer in a cloud. So you can use quantum computer like any other normal, almost like any other normal server in the cloud. And IBM is, for example, IBM is offering free quantum computers. Some older and less advanced models are free to use. So not only that quantum computers exist, they are you can use it in a cloud and you can use it for free. So it's reality today. Quantum computing is reality. But unfortunately, there is no quantum advantage yet. So what means quantum advantage? Quantum advantage means that we can perform some computation faster, with lower cost, with less energy consumption, or with better quality and precision. So today we still don't have quantum computers are still not better, not faster than classical digital computers. So the speed up and this quantum advantage is still theoretical. We still didn't reach the point where quantum computers are better, but this is improving every day, almost every day. And every year we have new, not only year, almost month to month, we have better and better quantum computers and better solutions. So this is, and I will tell you why. So why we don't have a quantum advantage yet? One part of the problem is that quantum hardware is imperfect. So in quantum computer, we are manipulating with quantum mechanical phenomena, with quantum mechanical effects, and this is by definition already, how to say, quantum mechanics is strange by definition, and we are trying to precisely control quantum mechanical effects, and this is extraordinarily hard. And I can tell you that quantum computer is one of the most advanced piece of technology that human hand made ever. So and it's not surprising that we have noise. We are struggling with qubit count. Qubit is basic unit of quantum computation. So we are struggling with to make all these parameters, to improve all these parameters, to reduce noise, to make more qubits, to make qubits to live longer, to have interconnectivity between qubits, to have fidelity of programs that execute on quantum computer, and so on. So quantum hardware is imperfect, but it's improving as I said, almost every month we have some new something new in the industry. All those companies and big techs are working to improve quantum computers, and this is part of the problem why we don't have quantum advantage yet. So theoretically, it's very powerful. It's much more powerful than classical digital computers, but in practice, we are not there yet, and quantum hardware is part of the problem. Second part of the problem is quantum software or quantum algorithms. So we have only a few promising quantum algorithms. If you are following quantum computing, maybe you know for Shor's factoring algorithm, which is threat. Which could possibly someday break encryption, which is used on the internet today. So, for example, this is Shor's factoring algorithm. There is Grover's search algorithm, which then we have like quantum phase estimation, variation, quantum eigensolver, and so on. We have those algorithms, but we have even more. So this is only a part of the list. But mostly problem with quantum algorithms that they are not. We are not able to run quantum algorithm of practical size, of size which classical computer cannot perform on today quantum computers because noise and because other problems. So some of quantum algorithms are not scalable enough, or even not possible to run on today devices. So we have hardware problem and we have software problem. And now this is very unexplored space. There is in classical computing we have algorithms which we are using for decades, and sometimes occasionally we have some new algorithms, some new improvement in classical computing, because this space is already a lot of research is done in classical computing. But in quantum computing, especially in quantum software, there is a lot of space for innovation, and we frequently have new quantum algorithms, and it's possible that new quantum algorithm will emerge, maybe today, maybe tomorrow, maybe in a year, which will be able to solve some real-world problem, to efficiently utilize quantum resources, which will be robust to noise and errors, because we have noise and errors in today quantum computers, which is scalable to practical problem sizes, which is very important, and implementable on available quantum hardware, which we have today. So this is the goal. We need to find better algorithms, not only better hardware. Better hardware is not excuse. Bad programmer will tell you computer is not fast enough. But good programmer will make program which run on slow computer or bad computer. So hardware is not the only problem. Okay. There is, because this is in title of my presentation, so let me tell you about, there is a $5 million prize, which is organized by X Prize, GESDA, which is Geneva Science and Diplomacy Anticipator Fund, and Google Quantum AI. And this competition will last 3 years. It started in January this year. Registration closes in June this year, so you have time to join if you are if you wish. And phase 1 submission deadline is November 2025. So you have 1 year and a half to, if you want to join quantum computing. If you join today, you have 1 year and a half until you maybe you can learn and submit your proposal until November 2025. So you have 1 year and a half. And this competition ends in January 2027. So this is interesting because you can directly, how to say, directly benefit from your innovations in this area. There are also other competitions or challenges. Let's say there is currently active. I don't have slide for that, but there is an active challenge by BMW Group and Airbus. Airbus is airplane producer, airplane manufacturer. So there are multiple active challenges where you can join and participate and possibly submit your solutions, your ideas, your applications, and so on. Now, when we know all of this, so let's continue with quantum computing crash course. So let's see how that mystic quantum computer works. I will try not to use physics at all and mathematics almost at all. I will not use. So let's try to see how to explain quantum computing very quickly and how to program quantum computer very quickly, from which you will understand how that, less or more, you will have a picture how that works, and you will know, if you are interested, you will know where to go, how to learn, how what you can expect from quantum computing if you are not already familiar. So let's start with hardest part, and after this slide I promise everything is much easier, but this slide is most important to understand. So let's try. We have 3 parts of the screen here. Let's see the leftmost part. So here we have 3 classical bits. So this is one register of bits, 101 in this moment, but this is just a one register of bits and of classical bits. And bit can be in 2 states, of course, 0 and 1. And when bit is 1, it is 100% 1. When bit is 0, then it's 100% 0 or 0% 1. So bit can be 100% or 0%. It cannot be nothing in between. If you set bit to 1, it will be 100%. It will not change. If it changes, then your computer is malfunctional. You need to change your computer if this is not the case. So it will be 1 until it loses power. So in order to show to express or to, how to say, to express the probabilities of classical bit register, we need n bits. We don't even need real numbers to show probabilities of finding bit in some state, because that probability is either 100 or 0. So it's 1 or 0. So we need n bits. For n classical bits, we need n bits. Now let's go to this middle part, and let's say that we have spinning coins. When you toss a coin is spinning, and while coin is spinning, it's not, and let's say that head is 1 and tail is 0. So and when coin is lying on the table, it's head or tail, so it behaves like classical bit. But when coin is spinning, then we have it's not head, and it's not it's not tail. It's spinning. We don't know until we stop the coin. So while coin is spinning on the table, we have only probability that we will find coin in, for example, in head. When we stop the coin, that it will finish as head. So it's to express probabilities of a coins, we need three real numbers. Usually for coin, it's 50-50, so it's 50% head, 50% tail. But maybe we have some, I don't know, cheating coin which has 80% probability of head and 20% probability of tail. Anyway, for three spinning coins, or for n spinning coins, we need n real numbers to express probability of this system, let's say system of these 3 coins. And important to say here, as a introduction to last part, important to say here that when we stop first coin and we find it in state of head, for example, we don't know in which state we will find second coin. It can be the probability of second coin is not related to first coin. So if we stop first coin as a head, second coin can be either head or tail. It doesn't depend at all on first coin, and the same is with third coin. So probabilities of spinning coins on the table are not related one to each other, and this is why it is enough to have only 3 real numbers to express probability of finding head or tail for these 3 coins. Okay, now let's talk about qubits. Qubits are basic units of quantum computation, and usually for qubits we are using elementary particles. This can be photon, can be electron, or some other quantum system in superconducting quantum computers. This is Josephson junction, and I will not talk about that. Let's imagine some elementary particle, and let's talk about some property of elementary particle which can have two outcomes. For example, photon can be vertically and horizontally polarized, so you have only 2 outcomes. Or electron can be spin up, spin down, or spin down. And let's take one of the outcomes. One of the outcomes as 1, and other outcome as 0. So this is very similar to coins. We have head is 1, tail is 0. Here we have, for example, spin up is 1 and spin down is 0 with let's say with electron. But anyway, this is qubit. So let's talk about qubit, because qubit is in quantum computer. Qubit can be some elementary particle. And let's say that we have 3 elementary particles, and elementary particles have a property that which is called superposition. And superposition is state in which elementary particle is not in one state, it's not in another state, but it's some mix of those 2 states. And we, as an observer, we can assume, or we can think about it. This is simplified explanation, but we can think about it it's similar to spinning coin. So let's say that we have electron which is in superposition and of spin up and spin down. So it's not spin up, not spin down. It's both, if you want. It's and we don't know until we measure. The same as with coin, we don't know is it head or tail until we stop the coin. The same with qubit. So we don't know is it 1 or 0 until we measure the qubit. And until now, this is similar to spinning coins. So it's similar. So we have let's say three qubits, all three in superposition. And when we measure, when we stop, how to say, not stop, but in quantum physics, we say measure. So when we measure, we will get outcome of 1 or 0. It's similar to spinning coins, but in case of elementary particles, it is not enough to have, for n qubits, it is not enough to have n real numbers. Why it's not enough? Because probabilities of individual particles can be related. And let me go back to spinning coins. So elementary particles can enter into relation, which is called entanglement, in which when you stop, for example, when you stop this first coin and you measure tail, if second coin is how to say, is entangled with first coin, you will measure head as well from second coin. So the outcome of first qubit can be in relation with second coin. So when you measure second qubit, sorry. So when you measure second qubit, you will get the same outcome. Not necessarily, but we can put qubits into that relation. We can entangle qubits. This is called entanglement. So entanglement is relation between probabilities of individual qubits. Example is, so here is the example. We can have, for example, we have all three qubits to be 0 with 50% of probability, and all three qubits to be 1 with 50% of probability. So when we measure these three qubits, when we measure first, second, and third, we will get all three zeros, or we will get all three ones, but we will never get any other outcome. To express that, we cannot express this relation with only three floating point numbers, or with only three real numbers. This is why we need 2 on n numbers. So for three particles, so for 3 qubits, we need 2 on 3, which is 8. We need 8 numbers. For every possible outcome, we have probability. And in quantum computer can manipulate individual particle, superposition of individual particles or qubits with individual qubits, and also quantum computer can change the entanglement between qubits. So we can entangle or disentangle qubits. We can put qubit in superposition. We can remove it from superposition. And with quantum computer, when changing those superposition and entanglement of individual qubits, we are modifying this vector. And by performing this simple operations on quantum computer, we can change this entire vector. It can have any value, any value here. Only limitation is that sum of all probabilities, sum if always is always 100%, because it will always finish in one of these configurations. So there is always 100% probability. Total probability is always 100%. And now, because this vector here can be very large, if we have 272 particles, the size of this vector is the number of elements in this vector is comparable to number of atoms in observable universe. So this can be very, very large vector. And with quantum computer, we can, by manipulating individual particle superposition and entanglement, we can change with one operation, or if you want, with one CPU cycle, we can modify entire vector, which is giant. And quantum computer is actually not storing this vector. There is no, it's not written into quantum computer. This vector is only mathematical abstraction of what we can read from qubits. So, and this is where power of quantum computer hides. So this is where power is coming from. It's coming from superposition and entanglement. Now, I believe that this is confusing. Let me see if there are some messages here. Okay, so this is good question. Yes, this is just example. So this is not always. Some member says, is this probability just an example, or it is always that once you look at the qubit, the rest will have the same value spinning up? No, no, this is just example. We can put qubits into any. We can put qubits into any. How to say, into any probability, into any relation. Let me give you more examples, so it will be more, how to say, it will be more clear. I will show you a few examples of a state vector. One thing that I didn't say is that the probability of each outcome, if each possible outcome in quantum mechanics of a quantum system is actually a complex number. So we have a real and imaginary part. And in previous slide, I was talking about probability, but this probability is actually only outcome which we can read when we measure the quantum system. But the probability of quantum system is actually expressed with vector of complex numbers. To explain why this is complex number, it will take a long time, and we don't have that much time in this short presentation. But for you, from software perspective, it is enough that you understand that this is a vector of complex numbers, which all sum to 1. Sum of all numbers is 1. So this is a unit vector. And this is enough. You don't need to bother yourself why this is complex. Of course, more you learn, the better. But the same as you don't need to understand how car motor works, you can only sit and push the pedal and drive. And in the same way, you don't need to understand why this is complex number. It's important to understand that it is complex number. Why you will learn later. Anyway, so this leftmost, let's look at this leftmost example. So this is just 3 examples. We have this binary is possible outcome. So this is 3-qubit state vector. All 3 qubits 0 is 100% probability to have all 3 qubits 0. And this state and all other probabilities are 0. So this state is called 0 state. When you turn on quantum computer, it before you start executing anything on quantum computer, when it is in ready state, quantum computer is set in this 0 state. First element is 1 or 100% probability, and all other possible outcomes are 0. This is called 0 state. Then we have this GHZ state, which I showed in previous slide, in which is hello world of quantum computing. You know, in programming languages, there is always that hello world program, which is first program that you write in some language. In quantum programming, the first program that you will write will be this GHZ or Bell state with 2 qubits, or more general GHZ state, in this case with 3 qubits. So this is in fully entangled, 3 qubits, fully entangled, and in maximal superposition. And this is that outcome from previous slide, where we have 50% probability of reading all zeros and 50% probability of reading all ones. Okay, now this third vector is just some random state, nothing special here. Good to know is that both real and imaginary part can have value. Here I don't have imaginary part in vectors, but both real and imaginary part can have value and can be negative as well. But probability is of course always positive when you and you get the probability when you take absolute value of this complex number. Absolute value squared is probability, and sum of all probabilities is always 100, is always 1 or 100%. So this is how state of a quantum computer looks. And you can think of a state of a quantum computer as something that is, let's say, equivalent to memory of classical digital computer. It will be more clear later.
Can we stop and go back one slide, because people are asking questions about it. So we do have one question from Jovan saying, you can read in the chat, so we can have like 001 for 30%, 101 for 20%, and 111 for 50%. So that's a question, and people probably would like to look at the previous slide one more time to clear up their picture.
Yes, Jovan, we can have that state. We can have any state you can imagine, as long as the total sum of all outcomes is 100%. I hope that it answers the question.
You can now go to the slide with the bits. Yeah, that one. Aaron, if this is the slide that you requested to see again, do you have any questions about this one?
Are you here, Jana?
Yes, I'm reading the question right now. Taivo, if I'm pronouncing your name correctly, could we leave this question for the end of the session so we can get into discussion later?
Yes,
Oh,
I will explain how close we are to the breaking encryption. So it will be somewhere near the end, and you will also have, of course, have opportunity to ask. Now I see that we already spent 1 hour. Time is ticking. I have few more slides, so let's continue.
yeah, I believe we can continue.
Okay. Now this is state of a quantum computer, but what is program? Before we go to program, just to say that similar to spinning coins, we cannot directly access probability. So coin is spinning, we don't know what is probability. When we stop the coin, we will get outcome of head or tail. But from that outcome, we don't know what was the probability of having head or tail. Now, in order to learn what is the probability, we need to repeat that many times. So if we 100 times spin the coin, toss the coin 100 times, and statistically we will get head, tail, tail. And at the end, it will be somewhere about 50-50, hopefully for spinning coins. The same with qubits. When we measure quantum state, qubits lose that superposition and lose the entanglement. So when we read state, all we can read from quantum computer, from quantum state, all we can read is this bit string. And in this case, the most probable outcome is 0, 1, 1. This is just some random vector, but it has probability of 33%. Others are less probable. But intentionally, here I put that outcome will be 101 because there is also chance that it will be 101. And if we repeat the same experiment, if we repeat 100 times or 1,000 times, then we make statistics how many times we get 0, 1, 1, 0, 1, all outcomes, then we will see that we will have in 33% of cases, we will have this 0, 1, 1 outcome. So important to understand that similar to spinning coins, we don't know, we cannot directly read state of a quantum computer. This is very limiting factor, but what we do, we run program many times and get the outcome, and then we statistically reconstruct this probability, probability distribution. Okay. Now, quantum program. So state of a quantum computer is some vector. And this is usually shown as this Greek letter psi. And so only this middle part is actually a state vector. The rest is a helper that I put to be more clear. But you actually have only this middle part. So we have initial state of a quantum computer, and we need to transform that state into some new state. So state of a quantum computer is always unit vector. It's only question how probabilities are distributed through the vector. And so we are transforming unit vector into another unit vector. And equivalent to that transformation is matrix vector multiplication. So quantum program is actually matrix. So quantum program is not even similar to programming digital computers. quantum program is matrix set of matrices. I will explain more later. Which transform our state of a quantum computer. In this example, we have two qubit quantum computer, which is in zero state, in initial state, and we perform some quantum program, which will put our quantum computer in that hello world state where we have maximum entanglement and maximum superposition, equal superposition. So, and now quantum program is equivalent to quantum program is matrix. Now, because quantum computer cannot execute arbitrary matrix, quantum computer can execute only a small set of matrices, which is instruction set of a quantum computer. So we need to assemble our matrix out of small subset of matrices supported by quantum computer. So in this case, I decomposed this matrix into three smaller matrices, and in quantum computing, matrices have names. And for example, this matrix here is called Hadamard. So this is Hadamard matrix. This is identity matrix, which we all know, and this is C naught or controlled naught or controlled X operation. So in quantum computing, we have names for matrices, and this symbol here is a tensor product. So by multiplying 2 by 2 matrix with other 2 by 2 matrix, we actually get a 4 by 4 matrix, which is then dot multiplied with this 4 by 4, because our vector is four element vector, so we need a matrix 4 by 4, and because dealing with matrices will be very complicated. So for human, it will be impossible to do especially with larger matrices, and we have matrices can be giant, So because that every matrix have symbol, and in quantum program can be expressed as a quantum circuit, this handy diagram where we have qubits. So these horizontal lines are qubits or individual particles, and these symbols are actually matrices. For example, this H box is Hadamard matrix. This identity matrix is not shown. It should be here, but identity doesn't change anything, except it makes our tensor multiplied Hadamard makes it bigger. But identity is here, and we have C naught, which is this symbol. So in quantum programming, we have symbols for every matrix, and instruction of a quantum computer is matrix. This is important to understand. And now this diagram is handy for human. It's readable for humans, but in order to execute it on a quantum computer, we need to write it in form of a code. And in this diagram, you spot that I added two more symbols. These two symbols, these symbols are measurement. So this is measurement. So we have two qubits, qubit 0 and qubit 1, which start in a state of 0, in 0 state. We perform Hadamard gate. Then we execute C naught gate, controlled naught or controlled X, And then we measure first qubit, we measure 0 or 1, which will be written into this classical register. And then we execute or perform measurement on second qubit, where we will get 1 or 0. This is only index of a bit, which bit will receive the outcome. So this classical register will have after executing this program, this classical register will have value of 2 classical bits, which will be both 0 or both 1. And this can be expressed as in a quantum assembler. There is similar to classical computer in which we have assembler. In quantum computer, we also have assembler. This is QASM or open QASM. This is frequently used format for interchange between different quantum programming frameworks. So you can export from IBM into QASM and import into Google in QASM. So this is very handy format for interchange between different brands of quantum computers. And just to show you, so we have QReg. This is quantum register named Q. So this is Q register, which has 2 qubits. Then we have classical register named C. So this is the C register, which also has 2 bits. So this is 2 qubits. This is 2 bits. Then we execute Hadamard gate on qubit 0, Hadamard gate on qubit 0, and CX gate between qubit 0 and qubit 1. So CX gate between qubit 0 and qubit 1. And then we measure qubit 0 into classical register 0, qubit 0 into classical register 0, and the same with qubit 1. We measure qubit 1 into classical register 1. And this is a quantum program. Of course, this is Hello World quantum program. More advanced quantum programs are longer, but less or more, this is how quantum program looks like. And quantum program can also be written in Python. And it is usually written in Python, not in quantum assembler. Quantum assembler is handy for some use, but usually people use Python. This is example for Qiskit. Qiskit is IBM's Python framework. There is also Cirq. Cirq is Google Python framework for quantum programming made by Google. There is also PyQuil, which is Rigetti, and so on. So there are multiple and many Python frameworks. And this is how you write. And if you look at this Python code, you will see the very similar structure. We import some functions. Then we have we define quantum circuit. We add one quantum register, 2-qubit quantum register. We add 2-bit classical register. We define that, add that to circuit. We execute Hadamard gate. We execute CNOT gate between qubit 0 and qubit 1. Then we measure qubit 0 into classical register 0 and so on. And then we execute this job on a backend. Backend is, in this case, backend is simulator, but it also can be real quantum computer, which is in the cloud. And how many times we will read or how many times to repeat and read and get the outcomes, statistics of outcome of execution. So this is quantum program. Let me show you. This is 2 minutes to show you. So I'm using Quantum Programming Studio. This is free tool. It is on quantumcircuit.com. This is completely free tool. You can register and use it. In this tool, you can drag and drop quantum gates. So in this toolbar, you have quantum gates, and drag and drop to this editor. you can add measurement, and then you can execute that code, and we can see the state vector outcome of 0, 0 if 50% probability, and outcome of 1, 1 is 50% probability. And you can run that on real quantum computer and export to many different quantum programming frameworks, including Qiskit, Google Circ, Microsoft Q#, and so on. Let's export it to Qiskit. I will open it in Jupyter Notebook. So I will execute that program. And what we have is outcome. We executed program 1024 times, and we have 0, 0 495 times, and 1, 1 529. So if we execute more and more times, we will see that we have 50% probability of 0, 0 and 1, 1 outcome from measurement. Okay, let me continue. Time is ticking, so let's continue view. Okay, now I don't know how confusing is this or not, but I hope that you at least you have some vision on how quantum computer is programmed. So we are dealing with matrices and vectors. Linear algebra is your best friend when you are programming quantum computers. And it's not like, of course, you need to have knowledge of classical programming because you are dealing with Python, with, programming languages and whatnot. But programming quantum computer is very important to have knowledge of linear algebra and vectors and matrices. And all vectors and matrices are complex. So complex algebra is important, and so on. But anyway, so we now have some vision on how quantum computer works and how it is programmed. Now let's see how it interacts with classical computer. So we have CPU and QPU. CPU is, central processing unit, classical processor, and we have QPU, which is quantum processing unit. So we have some quantum computer in at top of the screen. Upper part is classical computer, and bottom part is quantum computer. In classical computer, we have some input data. We have some data that we want to process and to get output, to get some results. Now, what we do, so how we put that into quantum computer? Because quantum computer doesn't have something like input port. We cannot directly write into quantum state. All we can do is to make a quantum program which will encode our input data into quantum state. So our quantum computer is initialized into 0 state. Then, based on input data, which, for example, we want to add two numbers, 2 plus 2. What is 2 plus 2 on quantum computer? So we have numbers 2 and 2. This is our input. And we need somehow to encode those two numbers into quantum state. We make quantum program based on input data. We make quantum program which executes and prepares the state. So now in a quantum state, in state vector, we have those numbers encoded, and then main program executes, which adds those two numbers, and result is encoded into final state, into state vector, which we then measure. Potentially we repeat the same program many times. So we measure, we make statistics of what is the most probable outcome. then we decode that, convert from measurement outcome into output data. So for example, if you want to add 2 plus 2 on quantum computer, we encode 2 and 2. This main program performs plus or operation which we are performing, and stores the result into this state vector, which we then decode number 4, which is our result of our computation. This is how quantum computer is used with classical. So classical computer sends data, quantum computer executes and returns. Now this is, I need to say that this is challenging. So what are the challenges here? Challenge is how to encode data into state vector, because first of all, this state is unit vector. And for example, you have some picture or video or something that you want to process on a quantum computer. So how you will encode video into state vector, or audio file or some text. So you have text and you want to encode it somehow into. So first of all is to choose the protocol, how you will encode that into unit vector. How to assemble program which will encode your data into quantum state. This is also challenging, and potentially you will have a lot of small matrices that you need to execute, and with each gate or each quantum computer instruction, the error multiplies, or noise, noise multiplies in. So if you have a long program, or deep, as we say in quantum computing, the deeper the program, the noise multiplies, and simply you read random results at the output. So it's challenge to make as short as possible program which will encode your data, or also main program. So this preparation and main program executes in single shot, in single step. There is no this intermediate state. I added this state for clarity, but it all executes in single shot anyway. So when you have state preparation, the main program also need to have as less as possible gates, so to be as shallow as possible. And then from final state, we want to perform less as possible number of repetitions to get the statistics and to read our data. So this is challenging. It's not easy. It's challenging, but it's also interesting, and there is a lot of space from innovation and from improvement, because nothing is yet final and nothing is yet engraved into stone. So you have opportunity to contribute and to think how to perform all of these steps better, and possibly to reach quantum advantage. Why not? Why not you? Maybe you can do it. Just to add that there is two approaches. There is usually, so we have quantum, when talking about quantum algorithms, we have quantum only algorithms where input is encoded into quantum state, quantum program executes, and we read output directly from quantum computer. So this is what I showed in previous picture, and so this is quantum approach. But there is also hybrid quantum classical approach, or usually also known as variational algorithms, where we have a quantum program which is some universal quantum program. What means universal? Parameterized. So this is parameterized program which, by changing parameters, we can produce any unitary matrix. So this is not a program which is written specifically for the problem. Of course, it can be written specifically for the problem because you want to optimize this quantum program. But anyway, so this is some universal program, And input is actually input data, and output data never actually enters quantum computer. We only input is sent to objective function of which calculates the cost, and if minimum, so optimizer is minimizing some how to say some value, which if until it reaches it converts until it reaches minimum. And as long as we don't have a minimum, we update parameters of quantum program. We read quantum state, and we use that quantum state as a when calculating cost with input data, and repeat that as long as we reach the minimum. And then when we have the minimum, then we calculate the output classically. So these blue boxes and yellow boxes are in classical computer, and quantum computer is here to perform some to give us some vector which we are searching by updating parameters of a quantum program. So this is second approach. This is hybrid quantum classical approach. Both approaches have pros and cons. With quantum, I already said, challenging is how to encode data into quantum state, how to make quantum program for particular use case, and how to decode that data out from quantum computer. With hybrid approach, it's also quantum program is challenging because we need to as efficient as possible quantum program, but we are not writing quantum program specifically for the use case. We are only writing some so-called ansatz, which is quantum program which can give us set any unitary matrix for which we can use for our calculating our problem in optimizer. Problem here is number of parameters, because quantum program with many qubits have many parameters. So our optimizer is classical optimizer is dealing with many parameters, and also function is the objective function is actually Barren plateau, long story. So it's very challenging function to optimize. So here, when you scale up with small quantum algorithms, this is not a problem. But when you scale with many qubits, you have challenges with number of parameters, optimizer struggling to optimize, and so on. And so this hybrid approach is also challenging. So this is two most frequent approaches to solving quantum computation, how to say. Now, where are we now? So this is partly answers the question from one of our participants. What quantum computers can do today? So now let me show you. Everybody knows for traveling salesman problem, or maybe not everybody, but let's say, so you have list of cities, and you need to visit every city only once, and to come back to starting city, and in which order to visit cities, to spend how to say to distance to be short as possible. What is the shortest distance to visit all cities, in which order to visit? So this is a traveling salesman problem, and this problem has I think that it's factorial complexity. I'm not sure now, but quantum computer currently can solve only 5 cities. So this is something that you can do with pen and paper. You don't even need a computer for that. Unfortunately, quantum computer can do only 5 city solution. Classical computer can do much more. I'm talking here about optimal solution, because classical computers can do much bigger problem with suboptimal solution using heuristic approach. But using brute force, classical computer can make more cities, but more than quantum computer. So quantum computer is not there yet to do something useful in this for this problem. Now, integer factorization. So this is the question. Integer factorization is breaking encryption, because encryption is based on integer factorization. That is, for given integer number, find which two prime numbers to multiply to get given number. And in encryption, we are using like 256 or 2048 bit numbers, which are large numbers. And question is, I give you number, large number, tell me which two prime numbers to multiply to get that big number. And if you solve that, then you will break my encryption in very simplified words. So what quantum computer can do using this Shor algorithm, which is most popular algorithm for integer factorization, and something that is National Security Agency of USA is afraid that quantum computers will very soon be able to break encryption. I will tell you that with Shor algorithm on the latest IBM quantum computer, which is $1 billion computer, it can tell you, it can factor number 21. So latest IBM quantum computer can tell you that 21 is 3 times 7. Maybe, kids in the primary school can do that without quantum computer, without any computer at all. This is where quantum computing is today. So quantum computer can largest number, of course, using Shor algorithm. Now I can tell you that there are specialized quantum machines which can factor much bigger numbers, but those numbers are still not even close to size which is threat to security. So don't worry, you are secure from quantum computer today. But of course, it's good to be prepared, because quantum computing is advancing every day, and it's advancing in accelerated pace, and it's exponentially accelerating. So maybe tomorrow we will have number, I don't know, 2 million, factorized, then, who knows. But so it's good to be prepared. But for now, this is number that can be factorized with quantum computer. And third example that I put here is molecule simulation. This is simulation of minimum energy of molecular bond. So it's, by the way, it's unclear. It's unclear because different papers give different results, and questionable is accuracy, because we need chemical accuracy for these results to be useful. And what I found is largest I found is this methyl fluoride or fluoromethane molecule. This molecule is consisted of 5 atoms, you can see. And this experiment is done on with a lot of classical computation and preparation, and using many tricks. So this is the size of molecule that could be, maybe if this is not, if you look other papers, maybe you will see like methane, or maybe you will see some diamond, which is only carbon atoms, or something, but only few atoms, up to, let's say, up to 5 atoms. And in order to make cure for some drugs for some diseases, you need to deal with much bigger molecules. You need to deal with proteins, which are large molecules, DNA, which is largest molecule known to human. So we are not there yet to make cure with quantum computer, but this is advancing because only a few years ago the largest molecule was molecular hydrogen, which is smallest molecule in the universe, and there is only 2 atoms in molecular hydrogen, it's H2. Now we have this molecule, and tomorrow maybe we will have even bigger. So this is accelerating, but this is where are we today. Okay, what we can do to help these results to be better? This is question. So what we can do? First of all, it's important to choose a problem suitable for quantum computing, because not all problems are suitable for quantum computer. So it's important to choose the problem, and it's important to choose the real world problem, because there are some reports like Google supremacy experiment, where Google scientists in 2019, I think, or 20, I'm not sure, they made experiment which they claim that it takes 10,000 years for fastest classical supercomputer, which they made in 300 seconds, in 5 minutes. This experiment is useful because it shows that quantum computers are able to do something faster than classical computer, but that problem itself is not useful to anyone. So nobody will give you money for solving that problem. So this is a very abstract problem, and we need to find a real world problem that we can solve, which is suitable for quantum computer. To choose which algorithm to use, or to develop a new quantum algorithm, which is something that you can do, why not? To find how to efficiently encode classical data into quantum state, how to efficiently compile the quantum program for the target quantum processing unit, because every quantum computer have this different instruction set, different quality of qubits, and compiling quantum computer is challenging, and there is also a lot of space to improve and to innovate. So if you want to jump in, good place to jump in to stay classical, how to say, is to make compiler for quantum computer, more efficient compiler. Then how to decode data from the quantum state, how to deal with noise, because quantum computers are noisy, we said at the beginning, and there are a lot of efforts to make noise correction and noise suppression and noise mitigation and so on. So people are working a lot on to compensate noise, not only in hardware but also software, like kind of active noise reduction. And whatever you do, let's have a positive impact on society. So let's do something useful, not something that will harm people, but something that will help people improve our lives. So this is end of first part of my presentation, and I'm happy to answer your question.
Yeah, I believe right now is best moment to answer questions. You can stop sharing screen so they don't have to. Yeah, that's great. And there are questions in the chat. Would you like to read it by yourself, or do you want me to read them?
I'm okay to read.
Okay, perfect.
So let me go up to the
So the first unanswered question is when you go up at 1:23 p.m., it's is the potential graph you showed the current state of quantum computing. I believe that's a graph that you showed in very first slide that is showing time complexities of the problem.
okay. So question is, let me find the question. How to find it?
I could post it in the Q&A session, so or in the chat again, so you can.
Oh, I'm watching into chat. Maybe I'm looking at it.
I just posted in the chat. So can you see it now? Is the potential graph you showed in the? It's the newest message.
Yes. So, okay, I understand now. I see the question. The graph shows complexities of different algorithms that we already have for last almost 100 years. And the quantum computer is trying to move that from higher to lower complexity class. And quantum algorithms do have theoretical possibility to do that. So some quantum algorithms really can do that, but only in a small scale, which is not useful. How to say, like solving traveling salesman problem with 5 cities. If quantum computer doesn't have noise, and if we can encode it in efficient, and if many things, then quantum algorithm will be able to calculate much bigger traveling salesman problem than classical computer. But for now, because complexity is lower, it has much lower complexity, so it will perform much faster and in time that it's impossible for a classical computer. But at this moment, we can only solve 5 cities, or maybe there are some research papers where they reach 6, or I don't know, maybe, but for sure not 10. And 10 is already something that you can perform on classical computers. So even that would be not impressive. So answer to your question is that quantum computer can do that, but only small scale, which is not practically useful. I hope this answers the question. Feel free to ask more.
Definitely. Could you go into Q&A session? So my teammate is posting right now all the questions right there, so you can have them question by question to answer.
It says we have a problem. Please try refreshing the page.
Let me see.
Let me see. It asks me to reload. Maybe I will to refresh the page. I will try to refresh the page. Maybe it will be, the connection will be broken. I hope it will not. I will reload the browser.
Is it asking you? Okay, we are left without Petar right now. Okay, everything is great. You just need to unmute yourself. You just have to unmute yourself.
Okay.
Everything is great now.
I'm in QA session now.
Okay, perfect. I believe Kaylee posted most of the questions right there, how they arrived. So you can go from the end from the beginning, like scroll down, and then answer like how they appeared in the video session.
Okay, doesn't this look a little bit immature? In the classical programming, if you invent some format like XML or UTF, the first thing you do is to create libraries for encoding, decoding, parsing real-world data into the format that you invented. Okay, the challenge here is actually that we do have, so quantum programming frameworks do have functions to encode data into quantum state, but none of these methods are optimal. So I'm talking that there is a space for improvement and space for innovation, that we need to find a better way to encode classical data into quantum computer than what we already have. So answer is yes, we do have that. We do have libraries which do that, but it's open. It's open problem. So you are saying that there is no standard way to transform real information like number 10 into quantum state, and that everyone need to invent its own. No, that you need to invent your own. There is standard way, but we want to find a way to do it more efficiently, because converting number 10 is easy, but try to convert some matrix, multi-dimensional matrix, so it will be hard. It will be hard on a quantum computer. There is a library, but it's not performing well. You have space for improvement. This is not so smart question, sorry. How many states can 3 qubits theoretically have? This is a smart question. So qubits can have 8 outcomes. So 2 on n, which is 3 qubits, 2 on 3 is 8 possible outcomes. But how many states? You mean how many? Because the elements of that 8-element vector are complex numbers. So you are asking how many states, how many, this is how to say, this is not discrete, this is continual, because every element is a complex number which is continual, not discrete. So it's hard to answer. That depends on resolution of reading, of how to say, of resolution of manipulating that state of a quantum computer. So we can say not actually 3-qubit quantum computer is not useful at all. What 3-qubit quantum computer can do, you can do on your Casio watch, old-fashioned with calculator. So 3-qubit is nothing. We are talking about something useful above 30 qubits or 40 qubits. With 40 qubits, so the state is 2 on 40. Then this is starting to be challenging to simulate on classical computer. And with 50, 60, you cannot simulate. 60, 70 qubits, you cannot simulate. I mean, you cannot full state vector simulator. You cannot make full state vector simulation. You can make some tricky simulations, but full state vector simulations with 60, 70 qubits, you cannot do on classical computers because simply you don't have enough memory. I mean, supercomputer doesn't have enough memory. And we are talking about useful quantum program above 40 qubits or 50 qubits, let's say. This is some limit. 3 qubits, nothing. Okay, are H and CX matrices standard matrices to operate with? As I see, they were not defined in the Python program. Yes, H and CX are most frequently used gates in quantum programs, and you need to import those gates in Python. You need to import them anyway, even if those gates are frequently used. So depending on frameworks, maybe some framework has by default already, how to say, set of frequently used gates already imported, but yes, you need to import those gates. HSBC is currently working on a quantum secured method. Okay, so maybe I answered this question already. So banks and maybe, I mean, defense, military, and so on, they are preparing for quantum computing by improving security, improving encryption protocols, because quantum computers today are not yet able to solve, to break encryption, but possibly could be soon able. Now, it's not something that government and companies should be massively worried, because I said that largest number factor is number 21, so it's not that urgent, but it's good to start preparing, because in few years we can have that real threat of breaking encryption. Is this probability just an example, or is it always that once you look at the qubit, the rest will have the same value? Okay, I already answered that during the talk. What is potential application of quantum computing that you are the most excited about? I'm most excited about, for example, I would like to see something useful for humankind, which will directly impact all of us. And one example is cure for cancer. This is something that I would like to be a result of quantum computing. This is something, this is enters into that category of personalized medicine. It requires, because that cure could be seen as a computational problem, where there is a need to compute some chemical molecules, analyze DNA, find something that will, I'm not expert for that, but there is computational problems which potentially, when solved, could help to find cure for cancer. This is one big, how to say, something that I would like to see. But also energy production, clean energy, energy storage, and so on. So many other uses potential. I wish to see all the uses, but I don't wish to see military use of quantum computing. And unfortunately, in the past we have that the atomic energy is first used to make a bomb, and then it was used to make electricity. I hope that this will not happen with quantum technologies, not only quantum computing, but also quantum sensing and quantum communications. I hope, but military is also investing a lot into quantum computing, so who knows what we will get for that. This is what I'm afraid of. Do you have any resources you could recommend for beginners who want to learn more about this topic? Books accessible, and so on. Yes, so maybe you could start from Qiskit textbook. Qiskit textbook, this is, or you can start with, because this is Google, event organized by Google, there is resources at Google Quantum AI. So start by learning on Google Quantum AI. This is a good place to start, but I need to say that IBM quantum community is large, very large, maybe largest community, and they have a framework named Qiskit, which has many users. It's open source, and there is a very, very good introduction to quantum computing, which is Qiskit textbook. This is hands-on. This is a set of Jupyter notebooks where you can read and run directly in the cloud programs and so on. So Qiskit textbook is my recommendation for learning quantum programming. And also there are books and everything. So could Google provide us with an
That's an old question. Those
okay,
two you can skip definitely. We already answered them.
Okay.
You have one from Jovan, and I believe that's and one more in the beginning. That's it's saying, but quantum computing is solving the shortest path for 5 cities. What is the time complexity for those 5 cities?
Okay. This is hard to answer because algorithm that is used is variational algorithm. It is using a classical optimizer and repeating the process. So it's very hard to calculate actually. So I was trying to find the exact numbers to put it into presentation, but I couldn't. Because it depends on many factors. Depends on how you compile the program, how and so on. But paper says that the speed up is super polynomial. That means it's more than how to say. It's less than exponential, but more than polynomial complexity. So it's on somewhere between. So it's I cannot answer that question accurately. So I googled it, try to find the exact, but I couldn't. From Jovan, is quantum computing able to solve any simple but real classic problem like sorting an array, finding max in a set? On quantum presentation, usually show theoretical academic problems that find less than 0, but never some well-known algorithm that can be easily correlated with what everyday software application are usually doing. Yes, Jovan, thank you for this question. This is a good question, and usually people are solving and showing how to solve some problems that are not of practical use. One of the part of the reason for that is that not all problems are suitable for quantum computing. For example, sorting an array is not suitable for quantum computer. Maybe there will be algorithm, but it's not. One example would be I will also make one example which is useful. I hope useful. So we will after this session we have that practical session, which will be only half hour. So don't worry. We already extended to 1 hour to 2 hours. So I'm also a little bit tired from talking 2 hours. But I will show you one practical problem how to run on quantum computer one good example, which I will not do now. One good example is Grover search algorithm. You know, sequential search. In sequential search, the complexity is linear. If you have n keys on a key ring, if you have n keys, and you don't know which key is real key, you need to try up to n times. So you need to try every key until you find the correct key. And complexity is linear, so everybody knows that. So I'm talking about linear complexity. Okay, now quantum computer can do faster, which sounds crazy. How can you find faster than linear what is correct key? And complexity for sequential search is square root of n. So if you have 9 keys, the complexity, so you need to test only 3 keys out of 9 to find which is correct. Sounds crazy, but this is what Grover search algorithm do. But there is a catch. Catch is that it assumes that your problem is already encoded into quantum computer. So if your keys are already encoded into quantum computer, then you need square root of n to find the correct key. But if your keys are not already in a quantum computer, the complexity of encoding the problem into quantum computer is higher than that. So as a result, at the end, you will have complexity of more than linear. This would be something interesting. Maybe you gave me an idea on next presentation. I will make search faster than linear, sequential search faster than linear. Maybe that will be interesting to show to people.
Okay, thank you so much, everyone, for participating today. Thank you for staying for the whole lecture. It was my pleasure to have you, Petar, in the club. It was great. I'm sure we can collaborate more in the future as well. Thank you so much, everyone. If you have any question, please contact us on Google Developer Student Club University of London official page. And if there are any questions about the presentation, I will talk to Petar and provide you with answers. Thank you so much and bye.
Thank you. Thank you for having me here and for listening my presentation. And
It was
I hope we will make more presentations in the future.
Me as well. Thank you so much, Petar.
Okay.
Okay, bye.
Bye-bye.